Here's our Minidrone pulling off a full flip, and it's completely under control, no wobble, no loss of stability, no crash. This is what our controller is designed for: aggressive maneuvers, stabilization. Drones' popularity has soared in recent years, from surveillance to autonomous delivery to racing, but when they do fast flips, sharp turns, or recover from collisions, keeping them stable is really tough. That's why we focus on orientation or attitude stabilization control, especially under harsh environments. Now, to control the drone properly, we need to know exactly which way it's facing. That might sound simple, but in 3D, it's a huge challenge. You might have heard of pitch, roll, and yaw, the terms that are used to describe the orientation of a fighter jet, for example. Those are called Euler angles. When a drone flips too far, this angle can run into issues when being interpolated between two distinct orientations. It's like when a 3D model in a video game suddenly snaps or spins weirdly. That's called gimbal lock. And to avoid that, we use quaternions. Quaternions give a smooth continuous rotation in 3D space without any weird glitches, and this is extremely important if we want to generate complex orientation trajectories without having to worry about gimbal lock. Our low-level control method is based on sliding mode control, or SMC. It's designed to react quickly and remain stable even if there's noise, model error, or sudden movement. SMC works in two stages. First, in the reaching phase, the controller drives the system state towards a predefined surface. This surface represents the ideal relationship between variables like orientation or altitude errors and their rates of change. Once the state reaches this surface, the system enters the sliding phase. From here, it stays on that surface and slides toward its target state, even in the presence of disturbances or modeling errors. Our flight control system uses a cascaded multi-loop structure. We separate position control from attitude control, meaning the position controller computes a desired orientation and angular velocity, and the attitude controller tries to track those commands. For altitude, we use a single loop SMC. For most control problems, the actual states are not gifted, and so to make the control loop reliable, the controller needs to be able to sense things accurately. And for that, we use a nonlinear state estimator called the extended Kalman filter to predict the drone's orientation and altitude from noisy sensor data, giving the controller clean, consistent information to work with. We designed and tested everything in a high-fidelity Simulink model of a pirate Minidrone provided by MathWorks. In the sim, the drone can perform aggressive flips on both horizontal axes while maintaining full stability. Even under unusual initial conditions, the system tracks highly complex paths without losing balance.